have to switch to English because I'm going to talk about Dan. And I would like to embarrass Professor Mackenzie. So, Dan Mackenzie is probably the greatest living earth scientist today. And we're very honored that he's come here to give his talk. But, yes, but, Dan Mackenzie has been a friend of the ITU geology and geophysics groups for a very long time. I mean, I have known him for 41 years, we calculated the other day. But after I have come to the ITU, well, when I was in high school, Dan had published his famous 1972 paper on the tectonics of the Mediterranean. And all the geologists said, oh, he's completely wrong, because he drew this north-south fault. Well, everybody thought it was a fault. Only one person understood what was going on, and that was Ihsan-Ketin. And I would never forget, Ketin, I was a high school student, and I was talking to Ketin, showed it to me. He said, look, he said, this is good. And I will say it in Turkish, bu akıllı olan bu dedi. I will translate it now. When he first looked at it, of course, he knew Dan's status at the time and where he was in his professional development. He said, this is a clever boy. and after Dan came to Turkey for the first time, he met Professor Ketin, and they became very good friends. And when Professor Ketin passed away, I informed Dan, I telephoned him, and I said, Professor Ketin passed away. And Dan immediately said, I want to be a co-author on his memorial, he said. And he was. And Dan gave the first proper Ketin lecture here, and he was explaining that Ketin really had understood already in 1948 how to do continental tectonics. And while Dan was saying that, Yücel was sitting next to me, he sort of leaned over, he said, just to hear that, it was worth inviting this man, he said. Dan has helped a very large number of people here. I mean, Tuncay was in Cambridge, Sinan Özeren was taken by Dan to Cambridge, Haluk Eydoğan went to Cambridge. With James Jackson, we went to the field together. Dan often came here to give talks, and his support for the ITU group has been incredible. And Dan, we are very, very grateful to you. He also worked with Yücel. I think you are the only one here who actually published a paper with Dan. So, without further ado, may I leave the floor to you, Dan.
Well, thank you, Jalal, for all those kind words, which are not really deserved. When I came here, what I really wanted to do, and have wanted to do for a very long time, was to go to Eastern Anatolia, right? Because I have worked on the tectonics of Turkey since 1967, and I had never been right to the east, because all my friends said it is not safe, right? And now everybody said, oh, it's much better, you can go. So I then wrote to Jalal saying, I would like to go, is it safe? And he said, yes. And then he said, would you please give a talk, right, at ITU? And I had imagined that was going to be just a little seminar, right, of the people who were actually interested in the work that I am doing now. I had no idea, right, that I was going to be in front of an audience like this. So I should apologize, because the pictures I'm going to show you are very much work in progress rather than the final versions of the various slides which I'm going to publish. They're perfectly comprehensible, but in detail, everything needs fixing up so that I use exactly the same models all the way through and all that sort of thing. All the sort of details which I normally, in a professional thing, would never talk about in front of an audience like this. The other thing I should say is that this is the first time I have given a talk here without Jalal acting as interpreter. And I'm really delighted to be able to talk in my native language right in front of this audience. And I think that is a real luxury of which I'm very conscious, that my native language is now the language of science. And that is just an enormous advantage to people like me. I don't have to learn a foreign language, and I don't have to write in it. And so I will do my best to talk slowly. What that seems, having talked to people a lot, actually talking slowly is the thing which makes it easy for an audience to understand in English. So I will do my best to speak slowly. I generally, quite often when I'm talking in foreign countries, my wife is in the audience, and I tell her to put up her hand like that if I'm talking too quickly, which she does. So let me say, to start off with, that if I'm talking too quickly, right, will somebody in the audience just do that, and I will see if I can slow down. Because I get interested in what I'm talking about, and I then forget, right, that I promised to talk slowly. So with that as an introduction, what I want to talk about today is various things which I did not really realize when I started were connected. The first thing... Oh, absolutely, absolutely. You don't need my coat, I don't think. I think it's going to rain on the rector. Right. So, where are we? I want to connect quite a number of quite different things. And I want to start with something which I have been doing with John Rudge, who is one of the junior faculty at Cambridge. And he's a mathematician. And what we decided to do was to... Everybody for a long time has believed that the mantle is convecting. And I don't think I have to convince this audience that that's true. The question then is, what form does the convection take? And we began, and we at Cambridge did such experiments, of the simplest possible system, convective system, which consists of a layer of fluid of constant viscosity between horizontal plates. The bottom plate has constant temperature and is hotter than the top plate, which is also at constant temperature. And the fluid in between has constant viscosity. Now, I can't think of anything which is actually simpler than that. Now, that problem, when we started, that problem, when the convection was vigorous, was not tractable with even the biggest computers at the time. So what we did instead was to have tanks in the laboratory, and the tanks were about 1 meter by 1 meter by 2 or 3 centimeters deep. And with those tanks, we could make images, right, by shining light through these, of what the geometry of the convection was. And here is one of the pictures. This is actually from Parsons and from a paper by Barry Parsons and Frank Richter, and it must be in probably the early 70s, something like that. And here is an image looking down on the top of such a convective system. And the way it shows the convection is that where the light, you send in parallel beams of light, if it's hot, because the velocity of light in the fluid increases, decreases, no, wrong way around, increases with increasing temperature. So the hot regions act as defocusing lenses. And in contrast, the cold regions, the light moves more slowly, so they act as converging regions. And so these bright lines are regions of the tank which is sinking and which are cold, and the black lines are hot regions, right, which are rising. And you can see what the geometry is. It consists of regions here where all these cold regions come together, right, here, and similarly with the hot ones. And this pattern is known as spoke pattern convection, right? Spoke because it's like a bicycle wheel, right? It has hubs. Here are the hubs, and the hubs are joined by spokes. And the spokes are either hot or cold. And this is the form of convection that we would expect from this. This is the form of convection we found when we did these experiments with tanks. Right? But we couldn't measure. We could look at the geometry, which is called the plan form, but we couldn't measure even the temperature, because if you put a probe into this to measure the temperature, then the probe affects the convection. So we were stuck. We could see what the pattern was, but we couldn't see even the temperature. And the things that you can observe on the Earth are the gravity field, the surface deformation at the surface, where it's rising, it pushes the surface up, where it's sinking, it pulls the surface down. And also, and this is something I'm going to talk quite a bit about in this talk, the melting, the generation of basalt, or I shouldn't say basalt, the generation of melts. I will get into trouble with the petrologists if I call all melts basalts. This is not approved of by people like UGEL. So we couldn't do any of that, right, with the tank experiments. We could see what the geometry was that we were expecting. Well, nowadays, with powerful computers, computing has changed enormously. We can now calculate the temperature, structure, everything else about a convecting region, and we can calculate also what these pictures would look like if we shone light through the numerical calculation. And here is a picture from something John Rudge did, showing essentially exactly the same geometry as we got from the tank experiment. But now we can calculate the surface deformation, we can calculate the gravity field, and as you'll see in a minute, we can also calculate the melt generation rate. So we now actually calculate the three things that we can observe. And this has been a huge change. Right? So what I'm really going to talk about is what use we can make of the fact that we can now do these calculations. Oop. I should explain at the beginning that my computer, I usually use my own computer, but for some reason it won't boot. It says that it has not got a hard disk, and it just has done that really in the last few days. So I'm not quite used to using PowerPoint. This is a picture again from John Rudge, showing some of the observables. Here's the picture I showed you, right? This time right, of calculating the thing to show, and this is the pattern, these are hot, these are cold. Here is the surface topography, and I'm afraid this, at this stage, is a fluid dynamical picture, so nothing has any dimensions. Fluid dynamicists never put any dimensions on anything if they can help it, right? So this, the temperature in the layer varies from 1, right? From here 1 to 0, and the depth of the layer goes from 0 to 1, and the horizontal dimensions are simply measured in terms of the depth of the layer. And this is how fluid dynamicists, those of you who are fluid dynamicists like Sinan, know all about this, that you make everything dimensionless. And that makes the whole process much better, and it makes it totally obscure to people who are not fluid dynamicists. So I'm not going to try and explain either why they do it or what the results are, because I'm going to come out of this and turn it into real dimensions very shortly. But you can see that we can calculate the surface topography, and as you'd expect, where the thing is coming up, it pushes the surface up. If you compare the pattern here with what goes on here, you can see that these black lines here correspond to the red lines here. We can also calculate the gravity, and the gravity is less straightforward because there are two effects with the gravity, right? Where the material is hot, the density is obviously lower. So you might think that there would be negative gravity where the material is hot. But the surface of the layer can go up and down. You can see that in the surface topography. So there's another effect, which is that the surface is higher where it's coming up. And it's not obvious to anyone, I think, which of those two effects is going to be the more important. But everybody who's done these calculations has come to the same conclusion, which is that the surface effect, the pushing the surface up, is more important than the negative density because of the heat. And that the gravity, therefore, is positive over the rising regions. Those things I need you to remember. Not the actual values, that we're not going to be concerned with in this talk, but the fact that where the surface goes up, the gravity is positive. And the ratio of these two we can calculate from these experiments. So,
wouldn't you expect hexagonal patterns in the ITÜ space?
this is what we actually get in the tank experiments and the machine. We'll see in a minute that the geology looks like this, not hexagons. The reason, there are a number of reasons. I mean, yeah, all right, let me digress for a second about plan form. If you take a layer of fluid and steadily increase the temperature difference between the top, between the bottom and the top, at the beginning there is no convection. Right? When you reach a certain critical temperature gradient, the convection starts, and the way in which it starts is in the form of rolls. So just lines, this would just consist of lines. If you go on increasing it more, what then happens is you get an instability with rolls coming in at right angles to the first set of rolls. And that's called the cross-roll instability. If you increase it more, and here I need to be technical in terms of the Rayleigh number, once the Rayleigh number exceeds about 100,000, then the bimodal pattern that you get breaks down into this spoke pattern, which is irregular. You only get hexagons when you break the up-down symmetry of the initial thing. You can do that in various ways. The way which we used to do it was by using a fluid whose viscosity depended on temperature. And the one that we used to use in the laboratory is something which everybody who is English will immediately recognize. It was called Lyell's Golden Syrup. And this is something which every British child wants to eat for breakfast. And which for many years I ate for breakfast. Right. And it is it's like corn syrup, right? And its viscosity varies. You can just in a tank, you can make its viscosity vary by 7 orders of magnitude in a tank which is no deeper than 5 centimeters. So it was an ideal material. So we wrote to Tate and Lyell, who produce Lyell's golden syrup, and said we wanted to use it for tank experiments. And so they sent us gallons, something like 50 litres of this stuff, which we used. But it had one major disadvantage. It is a curious material. It is 83% sugar and only 17% water. And why it does not crystallize. And what I do know is that sometimes it does crystallize. You come back, after you go away in the evening, you come back in the morning, and you have a tank of sugar crystals, right, instead of a liquid. And then it's a major problem getting the sugar crystal out. Right. Anyway, that convex in hexagons, but that's a different. Anyway, so this is called spoke pattern, and that's what you get at high Rayleigh numbers. We think that the Mantle Rayleigh number is at least 10 to the 5th, and if it's whole mantle convection, right, then it's probably 10 to the 7th, 10 to the 8th. I'm not really going to talk about whether it's whole mantle convection or not. All that matters is that the Rayleigh number is really quite high, right? And so what we're expecting is spoke pattern convection. Yeah, please do interrupt me and stop me at risk of my overshooting my time slot, but I guess I will be forgiven. Okay, so now what we did, and this is the first of our real things, at the top, right, here is the gravity calculated and now scaled to the real world, calculated from one of these convection models. Right? And this is in, now the horizontal scale is now in degrees, and so is the vertical scale. Now, I was brought up as a marine geophysicist, so I never put scales on maps if I put degrees, because everybody knows, except that continental geologists work in such small areas that they don't know, right, that 1 degree is about 100 kilometers. So what you're looking at here is something, right, which is about 1,800 kilometers by 1,800 kilometers. So this is quite a large region. And we scaled the gravity, right, sorry, you can't read this very clearly, 40, 20, 0, minus 20, minus 40 milligauss. This is the surface topography from this model. And you can see this is rising here and here, and it actually spoke pattern. So you've got the sinking spokes running like this. And here is the surface topography, and here this is 500 meters, minus 500 meters. So this is all calculated. This bottom, the bottom one, is an area of Central East Africa. And I chose it because in that region there are large, Lake Victoria is in here. This is the Western Rift, this is the Eastern Rift. You can see here, and the gravity has been filtered to remove the gravity anomalies from directly from the rough. You can see it consists on the two things here of 2 large positive gravity anomalies and negative anomalies elsewhere. Here's the corresponding surface topography. And you can see that now we can do the calculations properly. We can see very clearly that the pattern that we're seeing in East Africa, it corresponds very well to the pattern that we get from the simplest possible model. No variations of viscosity, no nothing. Just simple convection there. So there's no evidence in this picture for any complications. Right? It really looks just like the simplest system we can have. And that actually I had expected, because with the Lyell's golden syrup, what happens is that when the convection is vigorous, the interior temperature is relatively constant, and all the huge variation of viscosity is expelled into the boundary layers. And that's just what we see on Earth. Right? We know that there's plates. We can make plates by having a very, very high viscosity just in the top layer. So the interior, right, of these convective systems looks just like constant viscosity. So that was not a surprise. But this then means that we can actually use the gravity to look at the convective circulation. Right? And the gravity we now have, I'm not going to explain how it's measured, but it's measured now, the really good gravity, the best gravity for these purposes, is from a satellite called GOCE. Right? And that's what it's spelled GOCE. But because it's a European satellite, right, and because the Italians are involved, right, it's known as GOCE rather than GOCE. Right? So here is the topography of the Eastern Mediterranean, smoothed, right, to remove the effects which are just supported elastically. I'll have more to say about the elastic support of short wavelength features later on. But for the moment, I'm going to remove those by passing it through a low-pass filter. And you can see something. None of this picture will surprise anyone in this audience. Here is Anatolia, and it's high. Here's the Eastern Mediterranean, and it's quite deep. It goes down to nearly 4 kilometers, right? And there's a steep gradient in between. Now, the thing about this area is that it's, as you'll see later on, I haven't actually got that picture. As I say, I apologize at the beginning for a rather random collection of pictures. But this is an area actually with some of the very largest gravity anomalies on Earth, right, in this wavelength. Right? There is a huge negative gravity anomaly over here, and an equally large positive gravity anomaly over Anatolia. So what I've done then is to say that these are convective gravity anomalies. I'm going to turn them into topography and remove that topography from the real topography. And you can see that the pattern is completely different. And in particular, Anatolia is now essentially at sea level. So the topography you've got here, right, in Anatolia, is the result of convection. The Eastern Mediterranean also largely disappears. So the negative topography, the depth of the sea, is the result of convective downwelling. Right? And both of these, I must admit, surprised me. I'd known about the gravity anomalies for a long time, but I hadn't realized quite how, until we had the GOCE gravity, I hadn't realized quite how clear this picture was going to be. So the first conclusion I've come to from all this is that the topography here in Turkey is very largely convectively supported. You'll see in a minute, there's a bit more to it than that, but that is basically the story which comes out of the gravity. Let me show you a picture of a larger region of the Middle East. This is, again, the gravity, this time also from Gauci, and the topography, again, smoothed. And you can see what's going to happen just by looking at these maps. You can see all this positive gravity anomaly coming up from the afar. Here is Eastern Anatolia. And you can guess what I'm going to say just by looking at the picture, which is that this is a hub, and this is a spoke joining them. And you can see that both in the gravity and topography. If I now remove the convective component of all this, right, then the topography, Anatolia, doesn't entirely disappear, right, and the topography in Arabia, but most of it does go also. In particular, this line which goes up here disappears completely. So what we're looking at here, right, is a convective support of essentially a spoke like that, actually runs more nearly north-south, and a hub here and a hub here. And last week, going around Eastern Anatolia, I had no idea as to how much volcanism there was there. I knew about the Afar, of course, but I had no idea that there were tens of thousands of cubic kilometers of melt in Eastern Anatolia. And that now, clearly in this picture, makes sense. That's a hub joined south with a spoke. Well, that's the picture from the gravity and topography. Now, what about melting? What we did, and this is again, I'm sorry, it's still got all the details of the calculations on the top. As I apologize at the beginning, this is essentially, I put it together because I thought this was going to just be a seminar in a room rather than of this stuff. And I didn't have time to do anything more. The black line here, well, first let me start with this part. Here is the temperature structure, right? When I take one of these convective models that I talked about, constant viscosity, and just put a lid on top of it. And the lid has constant thickness and a constant temperature gradient in the lid. Right? And the lid is what we call the mechanical boundary layer. So it's this part. Then below that is the convective circulation, and there is a boundary layer here, a convective boundary layer, which we call the thermal boundary layer. And then in the interior, the temperature is constant entropy. So it has what's called a constant potential temperature, right, in the interior. And here, the green line here is something which is absolutely constant entropy. And you can see the agreement between the calculated line and the green line is so good that the black line disappears beneath the green line. Right? So it really is quite accurately like that. And this, rather arbitrarily, we call the base of the thermal boundary layer. And you can see the temperature gradient here is conductive, right? The heat is conducted here. It's carried by advection here in the boundary layer and also in the interior. On here I've also put the solidus temperature, which is that thick back line, and the blue line is the solidus temperature of a material which contains 0.01% water. So it's just got a little sniff of water. And you can see that reduces the temperature, not by much. So this is the horizontal average of the temperature. What about the geometry looked at from the top? Now we're now looking down on top of it in the same way as we did before. So this is the plan view. And what we've done here is to calculate the melt generation rate from the fluid mechanics. So all these red spots are places where the fluid is rising. And as it rises, it melts. Right? because if I go back to this picture, you can see that if I come up here along one of these constant entropy lines, I hit the solidus. Right? So everywhere it's coming up, it's hitting the solidus and melting. And you can take that then, those results, and integrate it vertically, and so calculate the rate of generation of melt per unit area, right? And turn that then into a thickness. So this picture shows the thickness that the convective system will generate in 1 million years. And you can see that these hubs generate 30 kilometer thickness of layer in 1 million years. Well, that really, for any petrologist, is quite fast, right? And that's plenty to account for what we see in places like the Afar and eastern Turkey. But there's another feature of this which is very important, which is that these hubs are joined by the spokes here, all over the place, and it's a pretty non-uniform pattern. It's not regular, it's not hexagons or anything like that. And these spokes also generate melt, but not nearly so much. You can see here that this contour, this white, this thick black line here is 1 kilometer per million years in terms of melt generation rate. Now, what really surprised us was the extreme sensitivity of the behavior of these spokes to the lithospheric thickness. This one is calculated with a lithosphere 70 kilometers thick. If I now show you the next one, and I'll go backwards and forwards to these, this is an 80 kilometer thick lithosphere. So nearly all the spokes have disappeared. So if I go backwards and forwards, you'll see how different these are. So the question as to whether the spokes will generate melt is extremely sensitive to the lithospheric thickness, right? And that we had no idea about before we did these calculations. In passing, let me just say something about melt generation between really thick lithosphere, right? The thickness of the lithosphere beneath shields, like South Africa, right? The lithospheric thickness there is 200 kilometers. Actually, it's nearer. On global average is between 205 and 215. And this is run here with a lithospheric thickness of 200 kilometers. That's this one here. Here's the dry solidus, and you can see there's no possibility of melting dry solidus, right, with the upwelling. But the bases of these regions have very often been metasomatized by the addition of water and carbon dioxide. This is the solidus temperature, in this case, for something which has had 0.1% water added to it. And then you can see something quite different, which is that now the hottest part here intersects the solidus. So this also accounts for why you get very small amounts of melting, and you'll see the next picture how small they are. Look at the contour interval. We're now down here to rates of melt generation of 1 meter per million years, which is exactly what we want, right? Because the kimberlites, the volume of the kimberlites, for instance, somewhere like South Africa, is really small, right? And that's exactly what you'd expect if you try and melt things at the base of thick lithosphere, right? We know that these melts are from that sort of thing, because they bring up diamonds. This is the graphite diamond stability. You can see these melts are being generated within the diamond stability field. So everything is fine from that. Now, the other thing we can do nowadays is we can use the composition of melts to find out about how much melt was made and what depth it was made. And we do this by using, at least I do this, by using the rare earth element concentrations. And I wrote a great big program, which now runs, if you print it out, to about 500 pages, right, which will do this. It's relatively easy to use, but the trouble is I am now an old man. The program is written in various Fortran versions, with some of it still in Fortran 2. Right? And I said that most people are not aware that there was such a language of Fortran 2. It is a horrible language because it does not have a logical if, right? And anyone who writes programs, right, knows that if you don't have a logical if, you just generate spaghetti. Endless numbers for statements and to where it goes to. So it's a real mess. But it's backwards compatible. It works fine. But whenever I have graduate students who know anything about programming, they say this is a disgusting program because it's in Fortran 2. And I say, but it works. So anyway, that's most of it is in Fortran 77. But even that is now such an old language, and the way in which I program uses really depends on common statements, and that's really not allowed nowadays. People don't use common. Anyway, enough of that. What it allows me to do is to take the observed concentrations here of a whole series of rare earths and fit that to a melting model. And here is the solid line. This is the solid line. This is the melting model, which corresponds to the line which is going through those points there. Right. And you can see the fit's quite good. The way in which we describe these things is in terms of a potential temperature. And for those who know what that is, that's fine. If not, you don't need to worry. It's just a number which tells you, right, what the melting is going to look like. And the melting here corresponds to a potential temperature of about 1500 degrees centigrade. So simply from the melt compositions, we can get the melting temperature. And that I've done for a whole series of volcanoes and melts across the whole of the Eastern Anatolian Plateau. I haven't yet gone far enough north, right down to the Afar. And this is now superimposed on a temperature slice here through this area at 125 kilometers. You can see that in the east, the lithosphere, right, is thick enough that the temperature here actually is quite low. It's too low to melt. But where there are volcanics, you can see these temperatures, which are about 1550. Here is the 1560 line from the surface wave tomography, and you can see that that melting accounts really rather well for both the geometry of the melt generation here and also the temperatures. So the whole picture now fits together rather well, in my view, right? As you saw from the gravity and topography, this looks like a spoke, and now we can actually get the temperatures from surface wave tomography and from the volcanics. We can see very clearly that that is indeed what's going on. ignored it. Ignored it.
Another story.
Oh, no. I should say that these are only things with more than 8% MgO, right, in the melts. Right. The amounts of melt, I go back one, this is fairly typical. You can see the amount of melt involved is about 10%, right? And if you're making that much melt, the volatiles really don't matter, right? If you're making little bits of melt, if you cut it off here, then you get this line here, you can see up there, and that matches the most extreme of these, and that probably is affected by the volatiles. But I don't think the larger amounts of melt, which is what we're seeing here, are affected by the volatiles. But I ignore the volatiles. I think I'm going to... No, all right, let me explain this one. You can't match everything that way. And particularly, things with really extreme concentrations of rare earths, and this is from a volcanic region of western Iran, they have really extreme compositions. And I tried various methods to match this, and the only way I could do it was by generating, first of all, a depleted source, right, which was essentially done by removing about perhaps 25% of the original thing to make something which technically should be described, right, as a Harzbarkeit. I have perhaps to do a side thing. The people who work with nodules, mantle nodules, right, they have a terminology, and what they mean by a Harzbarkeit is something which doesn't contain clinopyroxene, right? The IUGG set up a commission to decide on terminology, and they decided that they would restrict Harzbarkeits to things which had less than 5% CPX. But none of the people who work on nodules use the terminology decided by the International Committee. So I always have to ask people when they talk about Harzbarkeits, are you a 5%er? And why? It's completely mysterious to me that they would go to all the trouble of setting up committees and doing all this in order to come to an agreement as to what the terminology should be, and then they don't use it. And it really is not very helpful to somebody like me, a physicist trying to learn petrology, when they do things like that. And I would really put in a plea, right, for not redefining things. And the latest one that I have real objections to is the redefinition of a pickrite. I know what a pickrite is, but that's not what the IUGG decided. Anyway, never mind about all that. So first of all, I've got to make a Harzbarkeit, having had my moan, right? Okay, by removing, in this case, about 25%. So this, when I've done that, I'm left with something which has almost no CPX. Then I'm going to melt by a very small amount of melting. So it's essentially a metasomatic melt. And I add a few percent of that to the Harzbarkeit and make a new source and calculate its mineralogy, right? And this material then has a bulk partition coefficient which is extremely small, right? Because these elements are incompatible both in olivine and in orthopyroxene. And that's what you need to make these extreme enrichments. There's an extremely small partition coefficient. So you can make a very little bit of melt like this by melting it, and then it's exhausted, right? But that's exactly what you have. You have these volcanics which have very small volume in Iran, they tend to be in Mars, right, which are really small volume. And the same is true of kimberlites. This is what you need to do with kimberlites. And then, lo and behold, you fit everything and so on. Now, the reason why all this is worthwhile doing is because when you do that, you can then calculate the density of the source of these volcanics. And the one I just showed you is from Hamadan here in Iran. And these numbers on these things, I wish I'd had a bit more time to put a title on it. This is the density contrast between these source regions and the convecting upper mantle in kilograms per cubic meter, ignoring the temperature effect. So it's just purely due to the composition. We cannot get the density from the surface wave tomography. The surface wave tomography is really completely insensitive to this depletion. But we can get it from the composition of the volcanics. And this here, 60 kilograms per cubic meter, to most people that sounds rather small. But if you want to do that by lowering the temperature, right, so that you make this is lighter by that amount than the convecting upper mantle. If you want then to make it the same density, you would have to cool this by 500 degrees before it would convect. So these regions, right, these regions of depleted material, and you can see here at Cameroon, Hamadan, these are regions of depleted material. These are extremely stable. They will not join the convective system. And that's presumably why these shields with thick lithosphere, 200 kilometers thick, are convectively stable. I think I should skip the story about the elastic thickness, which is not really critical to all this. Let me just say a little bit about Africa in general. Here are the gravity anomalies of the whole of Africa, including the Eastern Mediterranean, and you can see these enormous gravity anomalies, negative and positive here. And that must be something to do with the fact that an ocean has been subducted here. Exactly how that works, I don't understand yet. But just simply the association, here, these green lines are the coast, and this is where an ocean has gone. And that clearly has left an imprint in the mantle of large objects with density, which is convecting. But what you can see here is that we were looking at the spoke and hub. Here's a hub, here's a hub, here's the spoke joining them up. There are lots of such things in Africa, once you actually know what you're looking for. Here's another one. The famous one is the Cameroon Line. It comes across here. You can see they're all over the place. Right. So the convective pattern beneath Africa is essentially hubs and spokes. Here is the surface wave tomography, and this again is the temperature slice at 125 kilometers, and you can see it here much more clearly. Right? Here's the one I was just talking about, going up from the afar. Here's the Cameroon Line, the Darfur. They're all over the place. Right? So this, not surprisingly, right, the pattern of convection is what all of us really 30, 40 years believed, which is at the Israeli numbers, that this vigorous convection takes the form of hubs and spokes. Right? And that really is, and that accounts, it seems to me, for both the melt production, the gravity, the topography, right, and also the surface wave pattern. So we've got a lot of now independent methods of looking at this, and they're all self-consistent. So I think we now finally have really quite a good hold on the nature of upper mantle convection. I've said nothing about how deep it goes. I've said nothing about transfer across the boundary at 670, right, at 670 kilometers. That's the stuff for a different talk. I have views on all that. I could produce pictures like that. But I thought that this area, that this particular set of slides was of more interest to this audience. And I will, at that point, I will close and I will happily answer questions. Thank you. Yes. Do you want to use this?
Right was math. I can see
does that work? Wait a minute.
I can see the. That's
Yep.
okay.
Yep.
I can see the hexagonal patterns for Africa, but you cannot see it up north because of subduction effects. So how do you take into the subduction effects into your model?
This is just simply a temperature slice at 125 kilometers. What is the cause of the temperature anomalies is a different matter. I haven't really said anything about that other than that they're convective. Now, how much of all this results from the subduction, which is now not going on in eastern Turkey, right, on any scale? We're not subducting an ocean. We may be shortening, in fact we are shortening, but there isn't an ocean going down. And remember that what I'm concerned about is the temperature at depth. Now, just simply shortening at the surface won't alter the temperature at 125 kilometers. So I'm not really, I'm going back to saying that all I do is make observations. If the observations are self-consistent with each other, which I think they are, then it's up to geologists, right, to then actually decide how it got this way. I cannot tell what it looked like even 10 million years ago. And that's something perhaps I should emphasize, which is that the upwelling rate in these hubs is really high. They come up at about half a meter a year. So even going back 10,000 years, right, you're talking then about something having moved 5 kilometers. And these melting zones are really quite thin. So if you go back 10 million years, it's a completely different story, right? There's no reason to suppose what the volcanism looked like in the Miocene bears any relationship to the present motions. These motions are much faster than we used to think. Yeah.
Yeah, can you invoke nicely the...
Wait a sec.
Well, I can chat, so that's okay.
Yeah, but remember it's being recorded.
So you invoke nicely the consistency between gravity, topography, and surface waveform tomography, right? The question I have is about the Aegean. In Aegean, the gravity data shows low anomaly, at the subduction I specifically mean, in the south. Is that correct?
Try again.
In the Aegean subduction, where Hellenic subduction name is there. But we presume there is a subduction under southern Italy in Calabria by various set of data suggest, and the gravity doesn't show such pattern over there too. There I question the self-consistency all over the Mediterranean.
There's no present-day subduction beneath the Calabrian arc. Look at the fault plane solutions. That stopped, right? It probably stopped because it ran into continental material. And the whole of that arc up, the whole of Italy, is now undergoing normal, right? And the Calabrian arc, yes, there's a slab there, but there's no ocean being overthrust, and there's no ocean there to be overthrust. So I think it's run into, I mean, what the whole of this area of North Africa, I have a job to see that far, but the same thing happened all the way around the Western Mediterranean, that there were subduction zones which peeled back until they hit the continental edge of the continent. And then they stopped. The most famous image of this is the Rock of Gibraltar, which is actually thrust out from the deep ocean over southern Spain. And all along the north coast of Africa, there is the same thrust out. The Western Mediterranean especially is very strongly time dependent. And presumably the same thing will happen in the East, that as soon as the oceanic lithosphere in the East is exhausted and has been subducted beneath the Aegean, then that will overthrust the margin of Africa and the subduction will stop. And that's what's going on here. This is not, I think one thing I've made clear is that I've tried to remove here all the gravity effects which are due to flexure. Right? Nearly all the gravity anomalies in subduction zones are due to flexure. Maybe let me go back. Here you are. This one shows the gravity without that removal. You can see it's much more complicated. It's rather hard to see what's going on. You can see it's all being bent here. This is from the subduction, well, the overthrusting of the Zagros. There's all kinds of complications, right? But if what you're interested in is what is going on underneath the convective pattern, then you've got to take account of the fact that the elastic thickness in some places here is very small. So here you don't need to filter. If you low pass filter, which I have been doing with a wavelength of 200 kilometers, then you're fine here. You're not so good here because the elastic thickness is much bigger in the northern part. So that's why you don't see what you're expecting to see. It's because of the filtering.
But did you apply a uniform filtering? I mean, if the elastic is small, means that you do the filtering or not filtering, it's more or less you see what's underneath, right?
I use 300 kilometers, which kills everything. Right. I'm sure if you're really prepared, the difficulty, as you very well know, is that in order to get this number, you have to use a box, and these are the boxes, so you don't get resolution within that, right? So, if you really believe you can work with smaller patches, you might be able to go to shorter wavelengths and still see the convective anomalies. But I mean, in the whole of this area of North Africa, it's the elastic thicknesses are really small, right? So we're all right, right? The elastic thickness goes up to about 25, 30 kilometers in Central Africa, where I showed that picture right before, and there you've got to be careful because the filter I'm using only just gets rid of that.
But well, I'm colorblind. I don't know what color this is, green or yellow. I see green. I think the region of elastic thickness larger than 30 kilometers. Are these boxes not too small to calculate elastic thickness?
These are done with profiles.
Okay.
The boxes, the green boxes, are done by stacking profiles and then fitting a different way. No, you can't. They're too small to do. Absolutely correct. Yeah. Yeah.
In the first couple of pictures, you have shown us the Mediterranean topography, the dynamic topography removal, and then you use that information to elaborate on the gravity structure. I was a bit puzzled. Could you elaborate more on how you calculated the dynamic topography? Did you use a constant lithospheric thickness? How did you treat the lateral variations of crustal and lithospheric thickness?
This one. The first thing is that this is all long wavelength, right? So the elastic thickness, right, and that I low passed both actually. The gravity, Gauche gravity is good to 200 kilometers, but I only used it to 300 kilometers. And I did the same, and the topography is from David Sandwell, so it's the shuttle topography on land. David gets, his topography in the oceans is much better than you might think. He gets tapes sent to him anonymously, right, with beautiful data on them, and he does not know where they come from. Right. Where they actually must come from is something like the CIA or the US Navy. Right. These are regions which, they have even better data, but they're prepared to give him data. But it comes absolutely with no labels, nothing. Right. So the depth variation in the Mediterranean, for instance, from Dave Sandwell is much better than you might think. So that's where that comes from. And I low-pass filter that as well. Now, because I'm working at a wavelength, in this case, I can't remember what I use. I think this is 300 kilometer low pass. I don't have to worry about the flexure. I have not corrected for the crustal thickness variations, right? I don't think they're very important because of what I showed you right at the end. Let me go back to that last one. You can see that there are lots of places here where there are crustal thickness variations. Look at, for instance, Somalia, the Red Sea, or the Western Mediterranean, whereas these anomalies are enormous, right? So I think most of that anomaly cannot be simply, right, the gravity field resulting from isostatic compensation. I think I haven't removed it. I said right at the beginning, I have not done everything I should have done, right? I had no idea I was going to have an audience like this. This is all Jalal's fault. But I don't think it'll make much difference because of the rest of it. And I should have done it, and I will do it, but I haven't.
Thank you. Let me call the proceedings to a close. Time constraints. We have about 20 minutes. I'm sure there are a few people who would like to say hello to Dan. So I will get up here. But Dan said it was my fault that the hall was filled to that extent. It's not true. And I tell you why it's not true by quoting my good friend Walter Pittman. Many years ago, Walter described Dan's research pattern. He said, Dan Mackenzie normally lives in the mantle. Now and then he surfaces, says something brilliant, goes back into the mantle. So, okay, I mean, it is the brilliant sparks that reach us have attracted all these people, Dan. It's not my fault, it's the fault of your name. But thank you. We're very grateful that at very short notice you agreed to come and give this talk. And we close the proceedings. Thank you for coming.